Hi everyone, welcome back to One Dimensional Kinematics, the adventures of Jim and Cindy, and this time we'll be working with problems involving acceleration.
Okay, so now we are starting to look at acceleration. Conceptual example number 6, a horse gallops with a constant acceleration of 3 meters per second squared. Which statement below is true? A, the horse velocity does not change. The horse moves 3 meters every second. C, the horse velocity increases 3 meters every second. The horse velocity increases 3 meters per second every second. So this is a strange thing. Accelerate 3 meters per second squared. Another way of looking at this is 3 meters per second per second. And what this means is every second it's going to be getting faster 3 meters per second. So the first second it's going 3 meters per second. The second it's going to be going 6 meters per second. Third second 9 meters per second, and so on. So what this is the horse velocity increases 3 meters per second every second. Okay. Example number 18. All right. Oh, there it is. Okay. All right. So back here, Cindy is about to get her permit and starts to shop around to look for cars. The salesman lets her know that the Audi R8 that she is looking at can go from 0 to 60 miles per hour in 3.3 seconds. Ooh, maybe she's pretty rich. What is the acceleration in miles per hour per second? Okay, so what you want to be doing in these kind of problems, well, first, it never hurts to draw it out. So let's just kind of draw out this car. We're going to kind of put a box with wheels. It goes from 0 miles per hour, and then it zooms in 3.3 seconds to a speed of 60 miles per hour. And we want to find what the acceleration is. So what we want to do with this kind of problem is we want to write down everything we know. So it goes from 0 to 60 in 3.3 seconds. What's the acceleration? So first of all, the initial velocity is equal to 0 miles an hour. The velocity final, it goes from 0 to 60, is going to be equal to 60 miles an hour. And it takes 3.3 seconds to get there. What we are looking for is we're looking for the acceleration. Once we write this down, what we're going to be doing is we're going to be looking at a formula sheet to find out the answer. In these acceleration problems, these kinematic acceleration problems, we want to always find the 3 values that we know and the 4th value that we're looking for. If we're able to do this, the problem shouldn't be that hard. So we're going to be looking at our formulas, and we're going to see which formula has all 4 of these variables. In this instance, it's this one right here. We're going to do acceleration is going to be equal to the change in velocity over time. Or acceleration is equal to the final velocity minus the initial velocity over time. So we can find the acceleration. We know the final velocity, it's 60 miles an hour. We know the initial velocity, it's 0 miles an hour, or just 0. And the time, which is equal to 3.3 seconds. So this simplifies to be 60 miles an hour every 3.3 seconds. And we can simplify this further, and we could do this 60 divided by 3.3, and we get 18.18. 18.18 miles an hour every second. And what this is saying is every second it's going to be getting faster and faster, 18.18 miles an hour. So the second it's going to be going 36.36 miles an hour, and so on and so forth. But now it's asking for what is the acceleration in meters per second squared. So this is where it becomes a little bit more difficult. So again, we have our values of initial velocity 0, final velocity 60 miles an hour. Time is equal to 3.3 seconds, and we're looking for acceleration. However, we're going to change the 60 miles an hour to be meters per second. So let's just do that. Let me use a different color for that. 60 miles. An hour. Let's get rid of the miles and put this into meters. And let's get rid of the hour and put it into seconds. So we know 1 mile is equal to 1609 meters. So we can get rid of that. And we know 1 hour is equal to 3600 seconds. So we get rid of the miles, get rid of the hours, and we get what we want of meters and seconds. Do a little bit of calculation, and we find that this is equal to 60 times 1609 divided by 3600, 26.82 meters per second. Alright, now that we know that, let's go back to our formula. Acceleration is equal to the final velocity, which is equal to 26.82 meters per second, minus our initial velocity, which is 0, divided by time, which is 3.3 seconds. And this simplifies to be, this simplifies to be 8.13 meters per second. So every second it's getting 8.13 meters per second faster. Or we could simplify this further to just be 8.13 meters per second squared. And important, what this is saying is every second it's getting faster 8.13 meters per second. So every second it's getting this much faster. And this, you're going to see this unit a lot, so make sure you understand it. Okay, next problem. Oh, wait, but what happened to the car? Did Cindy get it? Actually, her mom lets her know that she can have the 1995 Toyota Corolla instead. So no Audi, but anyway, she has a car, which is an important thing. Alright, conceptual example number 7. In which scenario does the car's speed increase? In which scenario does it decrease? In which scenario does the car have a negative acceleration? Alright, so we have scenario A, B, C, and D. So in A, we see that it's going to the right, the velocity is going to the right, and the acceleration is to the right. Whenever the acceleration and velocity are in the same direction, what this means is it's speeding up. In this case, we see that it's moving to the right, the velocity is to the right. However, the acceleration is to the left. Whenever they're in opposite directions, that means it's slowing down. Slowing down. Over here, again, we see that it's moving to the left, but the acceleration is to the right. Again, what that means is it's slowing down. Over here, it's moving to the left, but acceleration also to the left, same direction, which means it is speeding up. A lot of times in life we call it decelerating when it's slowing down, but acceleration can both be slowing down or speeding up. And anytime there's a change in velocity, that's accelerating. So it doesn't mean it's going faster, it can also mean it's slowing down. Alright, part B, in which scenario does the car have negative acceleration? So you might think, okay, if it's slowing down, that must mean that it has negative acceleration. But that won't be correct. What we have to know when it comes to acceleration is, whenever it's pointed to the left, like this case here, then it is a negative acceleration. However, whenever it's pointed to the right, like over here, it is a positive acceleration. So it doesn't matter if it's speeding up or slowing down, it only matters what direction the acceleration is going. If it's to the right, it's positive. If it's to the left, it's negative. Example 19. Let's go move this a little bit. Jim and Cindy decide to go on a ferry ride together as friends. Interesting. The ferry makes a short run between two docks, one in New Jersey, the other in New York. As the ferry approaches the New York, traveling the positive direction, its speed is 7.4 meters per second. If the ferry slows to a stop in 12.3 seconds, what is its average acceleration? So let me kind of draw this out first. We have the boat over here, and let's just kind of draw a little dock over here, and we'll draw another dock over here. Okay, so this boat is going, and it's riding along. It's riding with the speed of velocity is equal to 7.4 meters per second. And we're going to call this the New Jersey side, and this is the New York side. And we also know that it takes, so while it's going to take 12.3 seconds to come to a stop. So again, once we draw it out, we want to find everything that we know and what we're looking for. So we know that how long it takes to come to a stop is equal to 12.3 seconds. We know before it slows down, it has a speed of 7.4 meters per second. So at the beginning, it has a speed of 7.4 meters per second. And it seems like that's all we know. However, this keyword here is the ferry slows to a stop. What this means is that the final velocity is going to be equal to 0 because it's going to slow to a stop. Last thing is, what are we looking for? Average acceleration. So we're looking for this. Again, we're going to look at our formula sheet, and we're going to see what formula has all four of these variables. And again, we're going to be using the same formula here. This one has all four: acceleration, velocity final, velocity initial, and time. So now we can try to solve for this. Acceleration is equal to v final minus v initial over time. Acceleration we don't know, we're looking for. V final is equal to 0 because it comes to a stop. V initial is 7.4 meters per second. And time is 12.3 seconds. We do some math and we find that our answer is negative 0.6 meters per second squared. And this should make sense because if the ferry is going this way and it's slowing down, that means the acceleration has to be going the opposite direction. Okay, so it should be negative, which is to the left. Alright, now let's look at part B. As the ferry returns to New Jersey dock, its speed is 7.3 meters per second. If it comes to rest in 13.1 seconds, what is its average acceleration? So this is a little bit tricky. This is why you want to kind of draw it out a little bit. So again, this is New Jersey. This is New York. And now, the ferry is going back to New Jersey, meaning it's moving to the left. So the velocity is going to be negative 7.3 meters per second. We know for it to come to a stop, the time is equal to 13.1 seconds. And we know when it's going to come to a stop, because if it comes to rest, that means the velocity final is equal to 0. So now again, we want to do the same thing. We want to see what we have. We have velocity final equal to 0. Velocity initial equal to negative 7.3 meters per second. The time is equal to 13.1 seconds. And again, we are looking for the acceleration. We see we have the same variables as before. So what we can do is we can use the same equation. Acceleration is equal to the final velocity minus the initial velocity over time. Acceleration is equal to final velocity, which is 0, minus initial velocity, which is negative 7.3 meters per second, divided by the time, 13.1 seconds. And this gives us an acceleration of 0.56 meters per second squared, and it is positive. And it should be positive because if it's moving to the left, but it's slowing down, that means the acceleration is going to the right. And right is positive. Okay. Alright, next example. Cindy just got her provisional driver's license and is driving with Jim, cruising at 20 meters per second. After a while, Cindy decides to show off and step on the gas, accelerating at 2.4 meters per second squared. How fast are they moving after accelerating for 5 seconds? Okay, again, we want to draw this out. Okay, so again, we're going to just kind of draw it out with the box. This is Cindy, and she's cruising at 20 meters per second. She decides to show off, and she starts accelerating. So she's cruising, but then she steps on the gas. She steps on the gas for 5 seconds. Time equals 5 seconds. And she's accelerating also. Let me do it in orange, I guess. She's accelerating, going faster at 2.4 meters per second squared. And what we want to know is, how fast is this car going after that acceleration for 5 seconds? So we want to write down what we know. We know that the car is initially moving with a velocity of 20 meters per second. She's accelerating for 5 seconds. She's accelerating with an acceleration of 2.4 meters per second squared. And we want to know how fast are they moving after accelerating for 5 seconds. So we want to know how fast over here. So that's going to be the final velocity. Again, we're going to get our formula sheet and we're going to see what we're looking for. We're going to see which one has all 4 of these. And again, it's the same formula over here. We're going to get to more formulas, but for now, they're the same. Acceleration is equal to v final minus v initial over time. Acceleration is 2.4 meters per second squared, which is equal to the final velocity, which we are looking for, but we don't know, minus 20 meters per second divided by time, 5 seconds. All right, so we have to do some algebra. We're going to put the 5 over here, multiply it by 5, and then add this, put this 20 to the other side by adding by 20. And after we do some algebra, we can find that the speed that Cindy is going is 32 meters per second. Whew, she needs to slow down. Okay. Next question is, how far have they traveled at this time? So what we're looking for in this situation is we're looking for how far they traveled in this time. So we're looking for the displacement. So we want to find out, again, everything we know. Again, we know the initial velocity is 20 meters per second. We know time is equal to 5 seconds. Whoops, 5 seconds. We know acceleration is equal to 2.4 meters per second squared. And we know the final velocity is 32 meters per second. And what we're looking for what the displacement is. So now again, we're going to look at our formula sheet and try to find what we have. We can't use this one because we're looking for the displacement and the formula is not in here. And actually, since we have 4 variables this time, there's multiple ones that we can use. We can use either this one here, or we could use this one here. I'm going to use this second one over here. So what we have is displacement is equal to initial velocity times t plus 1/2 at squared. And then we have displacement We don't know what displacement is, but it is equal to the initial velocity, which is 20, times the time, which is 5 seconds, plus 1/2 a, which is 2.4 meters per second squared, times the time, which is 5 squared. Anyway, you should be able to do this all with your calculator, but if you have a hard time, just do this portion first, then this portion, and then you're going to get 130 meters. Alright, so what happens after this speeding incident with Cindy? Actually, Jim does not like this and begs Cindy to slow down, but Cindy only goes faster. Oh god, Cindy. Ooh, okay. We'll pause for now. Okay, example number 21. Jim and Cindy decide to enter an engineering competition. They need to build a toy plane that will be able to accelerate fast enough to take off the runway. The plane starts from rest, key point, starts from rest, and drives the length of the 15-meter runway. It needs to lift off at a speed of 20 kilometers an hour. How fast must the engine be able to accelerate in meters per second squared? Alright, so again, we want to draw out the problem. We see that there is a 15-meter runway. 15 meters. We have a toy plane that starts from rest, and then it needs to be able to take off at the end of the runway with a speed of 20 kilometers an hour. Okay? I believe that's everything. Important thing to know is this starts from rest, meaning the velocity at the beginning is equal to 0 miles an hour or 0 meters per second or whatever. What we want to find out is what the acceleration is. So let's write down what we know. We know initial velocity is 0. We know that it's going to have a displacement of 15 meters. We know it needs to take off at the end of the 15 meters with a speed of 20 kilometers an hour. And we're looking for what the acceleration is. Okay? And we want it in meters per second squared. However, before we can do this, we need to have all of our units correct. We have meters, but this is in kilometers per hour. So we can change this to kilometers. However, since we want everything in meters per second squared, I'm going to change this 20 kilometers an hour into meters per second. So I'm going to convert this 20 kilometers an hour. I'm going to change this to meters per second. So let's get rid of the kilometers and change into meters. We know 1 kilometer is equal to 1,000 meters. Whenever you see this K, it stands for 1,000. And then we know that an hour, 1 hour is equal to 3,600 seconds. Get rid of this kilometer, get rid of this hour, and we get what we want, our meter and seconds. Do a little bit of algebra, and we get that this is going to be equal to 5.56 meters per second. Okay, so we can change this to 5.56 meters per second. Now that we have all of our knowns and our unknown, we want to look at our formula, and we want to see, okay, which one has all 4 of these. This one doesn't have displacement, so we can't do that one. This one doesn't have final velocity, so we can't do that one. This one has final velocity, this one has initial velocity, displacement, and it has what we're looking for, acceleration, so we're going to use this one. Again, we're always trying to find the 3 knowns and the 4th one that we're looking for. And then you could solve any of these problems. So we can do velocity final squared is equal to velocity initial squared plus 2a change in x, and start filling it in. So velocity final is 5.56 squared is equal to initial velocity 0 squared plus 2 acceleration, which we're looking for, displacement, which is 15. Okay, so hopefully you'll be able to do the math of this, but we're just going to 5.56 squared, which is 30.91, is equal, this is just 0, 30 times a. So we do divide by 30 on both sides, and we get the acceleration as 1.03 meters per second squared. Okay, but what happened to the plane? Jim actually forgot to glue down the wheels to the axle and does not have a functioning plane. Cindy is not happy about this. Oh god, Jim at it again, just when things were going well. Cindy is frustrated and leaves the competition without Jim. She is driving on a road going 11.4 meters per second and suddenly sees a deer. Cindy immediately applies the brakes to slow down with an acceleration of 3.8 meters per second squared. If the deer is 10 meters from Cindy when she applies the brakes, does she hit the deer? If not, by how much does she miss it? Oh god, kind of a mess. Alright, let's kind of draw out this problem. So she's in her car, she left Jim by himself. She's in his car, it's kind of moving fast, 11.4 meters per second. 10 meters away from her is a deer. Oh god, deer. 10 meters away. She applies the brakes. So the acceleration is going to be going the other way, going 3.8 meters per second squared. And since it's going to the left, it's going to be negative. And we want to know, is she going to be hitting the deer or not? And this is a little bit complicated how we're going to do this problem. So we know before she applies the brakes, she's starting out going with the speed of 11.4 meters per second. There's a few ways to do this problem, but I'll show one way that I think is the simplest. We know when she applies the brakes, she's going to be accelerating with an acceleration of negative 3.8 meters per second squared. We know that the deer is 10 meters away, but we don't exactly want to use that right now because we don't know anything about this 10 meters. What we want to know is when she comes to a stop, is it before 10 meters or after 10 meters? So we want to know, where does she come to a stop? And when we know when she comes to her stop, the velocity final is going to be 0 meters per second. That being said, we want to find out how far she is when the car has finally come to a stop. So we want to find what the displacement is when the car is going 0 meters per second. Hopefully it's before 10 meters so she doesn't hit the deer. Now, again, let's look at our formula sheet and let's see which one we're going to use. Again, we're going to notice that this formula here is the one that has all 4 of these variables. So we're going to use our formula. Vf squared is equal to V initial squared plus 2a change in x. 0 is equal to 11.4 squared plus 2 negative 3.8 change in x. And then we find that the displacement is going to be 17.1 meters. And what this means is if she applied her brakes, her car would not come to a stop until 17.1 meters. So yes, she hit the deer. Oh no. Part B is, if she did hit the deer, with what speed did she hit it? Okay, so what we're looking for now is, at 10 meters, how fast was she going? So we want to know what the speed is at this 10 meter mark. So what we know is, again, she was moving at the beginning with a speed of 11.4 meters per second. Her acceleration is negative 3.8 meters per second squared. We want to find what her speed is after she has traveled 10 meters. And we want to find what this velocity is at the 10-meter mark. So we're going to be looking for the same, we have the same variables here. Well, not same, yeah, same variables, different numbers. And we're going to try to find what this velocity is after 10 meters. So Vf squared is equal to V initial squared plus 2a change in x. Vf squared is equal to V initial squared, which is 11.4 squared plus 2, acceleration negative 3.8, displacement, which is 10. Remember that this is squared, so we're going to have to find the square root of all of this at the end. But we should come up with an answer at the end of 7.35 meters per second. Okay. So what happens? Cindy cries in hysteria after hitting the deer and calls Harry for help. Oh God, what's going on?